This video will discuss working with similar solids. Just like planar figures, you can have solid figures, 3D figures that are similar to each other. How do you know they're similar? If they're ratios of corresponding linear measures, such as a height or a radius. So a linear measure, that's something you can measure with a yardstick or a tape measure or a ruler. It's how many centimeters or inches. For example, if I have a radius here and a radius here, that means that they have a scale factor ratio if they are similar figures of R1 to R2. And anything else you can measure in single units. So things like height, these will have that exact same scale factor ratio, just like any other similar figure that we've worked on in the plane. It's just now we're in 3D. So this shows what it would look like if you had similar cylinders. If they were not similar cylinders, things like the R1 to this R2 would not match the height of this one to the height of that one. So that would make them not similar. Let's review a little bit how this worked in the plane. If you have a set of similar polygons, say, and I know a scale factor ratio, in this case, A to B, if those are our corresponding sides, that means if that's C and that's D, that will be the same ratio. Now, if you want the ratio of their areas, you would take the square of the scale factor ratio. So if this is my scale factor ratio, then the area ratio would just be the square of that. So if you figured out this one's area, or if you knew this one's area, you could find this one's area by just setting it equal to this ratio right here. And I do have another video that kind of reviews how to do that if you want to watch that. So with solids, a lot's the same, but a little bit is different. Scale factor ratios work the same as they did with the polygons. If I have an R1 over here and an R2 over here, if these are similar cones, then R1 to R2 would be the scale factor ratio, and it would match anything else you could measure with single linear units. So height 1, height 2, that would be the same. Maybe you want to look at their slant heights. They would all have that same scale factor ratio, and those are single units, inches, feet, centimeters. Now, the area, surface area ratios, to compare surface areas, you look at the area ratio because surface areas are areas. So just like with polygons, if my scale factor ratio is some ratio A to B, then the ratio of their scale factors will be A squared to B squared. So this works just like it did with polygons. But we have another dimension here. We have this idea of volume. So you have a volume ratio as well. And the volume ratio is start with your scale factor ratio and then cube that, raise that to the third power. And that way, if I knew the volume of this one, I could find the volume of that cone by setting it equal to that ratio there. So it would be helpful to look at an example here, and I'm going to erase a little bit just because it's getting in the way. So scale factor ratio A to B, and surface area ratio A squared to B squared. Here is an example. I've got two canned products here. The cans shown have a scale factor ratio of 3 to 5. And I always write things down with a label because you're going to see a lot of ratios and it's very easy to get confused. So to organize your work a little bit, write the label down. This is the scale factor ratio. It's 3 to 5. Got it. The surface area and volume of the smaller can are known, and they're these values right here. They want you to find the surface area of the larger can as well as its volume. We're going to use our ratios to help us. If we're working with surface area first, surface areas are areas, so you're going to use the area ratio, which is just the square of the scale factor ratio. So I'm going to square that, and you square the top, you square the bottom. So that will be the ratio of the surface areas. I know one of the surface areas it's 40.73. I don't know the second one. That's what I'm trying to find. But I do know the ratio. It's this. Be careful, like any proportion, that you're going in a consistent order. So I'm going small to big here, small can to big can. So I'm also going small can to big can with this. That 9 times whatever that second surface area is 40.73 times 25. And then divide both sides by 9 to get my surface area. Put that in your calculator. You get approximately 113.1 square inches. That would be the second surface area. For volume, the volume ratio will be the cube of the scale factor ratio. So things to be careful that you don't do is you are not squaring that one. So don't square this. That's not the same thing. That's not what we're doing. We're taking the cube of this. So you take 3/5 and you cube the top and you cube the bottom. 3 to the third power is 27. And 5 to the third power is 125. If your cubes aren't up to speed, go ahead and use the calculator. You just put it in. I use the Desmos calculator. 3 to the third power over 5 to the third power. Kind of like this. We are just going to set up the ratio. So I know that V1 to V2, which is 17.16 to the thing I'm trying to find out, will be in this ratio right here. So you do the cross product. V2 will be 25 times 17.16 divided by the 27. It comes out to be approximately 79.4. And these are cubic inches because it's a volume. So this is 79.4. We can look at another example. We've got two similar pyramids. Pyramid P has a volume of 125 cubic inches. So I'm going to mark under here. I'm going to call that one volume 1 is 125 cubic inches. And I also know the volume of this one. It is 64 cubic inches. And it wants the scale factor ratio of Pyramid P to Pyramid Q. Well, I don't know that yet, but I do know the volume ratio. So again, I like to label everything I'm looking at. I find that just writing those words, volume ratio, and then putting what it is underneath is a very helpful thing to keep me organized. Scale factor ratio, that will be the cube root, because how did I get this? I took that scale factor ratio, whatever it was, and I cubed it, right? Going this way, you raise it to the third power. If I'm going the other way, then to undo it, you want the cube root. Unfortunately, this is an easy one to take the cube root of. But let's say you didn't know that this was the cube root of 125 is 5 and that the cube root of 64 is 4. If you didn't know that, you can use the graphing calculator to help you. And this is the Desmos calculator. That's what we use in Virginia. If you want to find cube root, one way to do that is to go by the functions button and you click on that, go to miscellaneous. And in there, you're going to have an N with a root symbol. In this case, I'm going to type in cube root. And then when I go over here, I'm just going to type in the fraction that I had there, which was 125 over 64. And it's written as decimal. I personally like working with the fraction so I can set up a proportion. And Desmos is really nice. Right next to this, there is a box over a box. That means turn that number into a fraction. And it only shows that if you can do that. It's 5 over 4. So use that calculator if you don't remember your cube root so well. Now, one thing I would like to point out is this could have said find, instead of scale factor ratio, it could have said find the area ratio. And if it had done that, I think the easiest way to get there is first do exactly what we just did, which is find the scale factor ratio. And then remember that the area ratio is the square of that guy. So that would be 25 over 16. There are ways to go directly from volume to area. They can be confusing. So my advice is if you have a volume ratio and you want an area ratio, or you have an area ratio and you want the volume ratio, go back to the scale factor ratio first, and then square it if you want an area ratio and cube it if you want a volume ratio. And really, that's all there is to this. It's just knowing which ratio to use and how to create those ratios. So I'm going to ask you to try these U-tries. And there are 4 of them actually. So if you don't have the worksheet that I give to my students, that's fine. Pause the video, do these 2, look at the results, and then pause the video again and do the last 2. So yes, pause your video, at least try these 2, and then start up when you are ready. And we're back. So hopefully you had a chance to pause and to work these out. Let's review them. We have cylinder A, and it's similar to cylinder B, and we're not showing it. If it's helpful, by all means, go ahead and draw in a cylinder B. Now, the scale factor of A to B, so scale factor, so the scale factor ratio is 1 to 2. It says find the surface area and the volume of that second cylinder, cylinder B. Let's set up our ratios. The area ratio will be the square of this guy. So 1/2 squared is 1/4. And the volume ratio will be the cube. Again, go back to scale factor ratio. Don't go to area. Go to scale factor. The cube of that, 1/2 cubed is 1/8. And if your cubes aren't so good, use the calculator to figure out what those cubes are. And then set up the correct ratio. If I want surface area, so this is surface area 1, that's volume 1, and I want surface area 2, volume 2. So surface area 1, 150 pi, to surface area 2 will be in the ratio 1 to 4 because they're areas. Surface areas are areas. I'll use that one. If you use the cross product, it'll be surface area 2 times 1, which is just the surface area of 2, equals 4 times 150 pi, which is 600 pi. And these are square inches. And I'm going to leave it like that because that's how they presented this one in terms of pi. So I'm going to present my answer in terms of pi. Now to find the volume, I'm going to do almost the same kind of thing. I'm going to set up a proportion, but I have to use the correct ratio. So the volumes, volume 1, which is 250 pi, to whatever volume 2 is, the thing I'm trying to find out, I'm going to use now the volume ratio of 1 to 8. If you do cross products here, that gives us a volume 2 of 8 times 250 pi, which, if I did it right, it's 2,000 pi. 2,000 pi cubic inches. Second example, very much the same idea. I've got 2 similar cones. They're showing me one of them, but there is a second cone, and if you want to show that one, if that helps you to see it, by all means, go ahead and do that. I have surface areas and volumes for the first one, but I want to find those values for the second one. We're going to do the same exact process that we did for the previous one. So they're giving me the scale factor ratio. A to B is 5 to 2. Find the other ratios. Find the surface area ratio by squaring that, and then find the volume ratio by cubing the scale factor ratio. So you go back here, which is 125/8. Then we can find our surface areas. So the surface area 1, 2, 3, 5, 6.2 to the second surface area will be in this ratio, the area ratio. If you do your cross products, 25 times S2 will equal whatever 4 times 2356.2 is. And then divide by the 25, you should get approximately to the nearest tenth. I got 377.0 square centimeters. And then the volume ratio, the volume we know to the volume we want. So that would be 7450.9 over volume 2 is in the volume ratio of 125 to 8. Do your cross product magic. You should get the second volume to be 476.9 to the nearest tenth cubic centimeters. These are the final 2. If you don't have the worksheet, go ahead and pause now and try these, but otherwise, let's go through them. We have two similar spheres here. Find the scale factor ratio of figure 1 to figure 2. So I know their volumes. So volume ratio is 8 pi to 125 pi. Now these pi's are going to cancel out, so my volume ratio is actually 8 over 125. To get to the scale factor ratio, we remember that we had to cube the scale factor ratio to get a volume ratio, so take cube roots to get the actual scale factor ratio. And remember, if they had asked for, here's the volume, go find the area ratio, you would still go to the scale factor ratio, and then you could square that to get the area ratio. They didn't ask for it, so it's okay if you didn't do it, but just as a reminder, that's how that would work. Got two similar solids here, find their scale factor ratios. So this time they're giving me their surface areas. So that area ratio will be 192 to 108. Now, here's where the calculator can really help. So the ratio I have for those areas was 192 over 108. So I'm going to type that in. And then I'm going to hit my turn it into a fraction button here, 16 over 9. So maybe you knew that by looking at it that we had nice perfect squares here, but maybe you didn't. I always like to simplify, and sometimes you get some good news, which we did here. It's 16 over 9. And why is that good news? Because the relationship between surface area and scale factor ratio is that you square scale factor ratio to get the surface area ratio. So to go backwards, you take square root, and it's nice having perfect squares. So that would be the scale factor ratio. If in this example they had said, here's the surface areas, go find the volume ratio, you would still go back, find the scale factor ratio, and then you would cube that if you wanted to get the volume ratio. Again, they didn't ask for that, and it's fine if you didn't do it. I'm just pointing it out. And that is basically it. I hope this is helpful when you're working with similar solids. As always, thank you for watching.